In this video, we're going to see how to actually find the stationary matrix for a regular Markov chain. So we're going to find the stationary matrix that we found previously by accident, kind of, from a previous video. So recall the example. So each day when I come to Camosun, I either bike or drive. If I drive, there's an 80% chance I drive again the next day. If I bike, there's a 40% chance I bike again the next day. So this example had this as its transition matrix, where the states were in the order D, B, so drive and bike. And we guessed, okay, that the stationary matrix was this, and then we were able to show that it was, in fact, a stationary matrix. We're now going to actually see how to find this. Okay, so let's just suppose that we have stationary matrix. So first of all, this Markov chain, I'm going to call that MC, is definitely a regular Markov chain, since all entries of P are positive. Okay, so P to the 1 has all positive entries. So we know it's regular. So that means that it has a stationary matrix. Okay, so let's call it, call this stationary matrix S. Okay, it's going to be a 1 by 2 because it's a state matrix, and it's going to have two entries. I'm going to call them, you can call them XY, or S1, S2. I'm going to call them XY because sometimes my S's look like 5s. So we know there is one, let's call it this. Okay, now since it's a stationary matrix, we know that it must satisfy the equation S times P equals S. Okay, so what does that mean? Well, if I take S times P, that's X times XY times my P matrix. Okay, and I should get my original matrix back, so XY. So if I simplify the left-hand side, so I do this multiplication, this is a 1 by 2, this is a 2 by 2, so I can do the multiplication, and I'm going to get a 1 by 2. Okay, so I take this row times this column. Okay, that gives me this entry. So that's going to be 0.8x plus 0.6y. Okay, and then when I do this one times this one, I get this entry here. And that's going to be 0.2x plus 0.4y. Okay, and that should be equal to xy. So if these matrices are equal, then in fact y has to be equal to this green entry, and x has to be equal to this yellow entry. So we actually get two equations. So I get 0.8x plus 0.6y is equal to x, and 0.2x plus 0.4y is equal to y. Okay, so I get these two equations. So these ensure, I made this thing too big. Okay, these ensure that S is a stationary matrix. Okay, but we also need S to be a state matrix. So a state distribution matrix, which means that its entries need to sum to 1. Need to sum to 1. Okay, so what that means is we get this extra equation, x plus y equals 1. Okay, so we need to make sure that that happens as well. So what I want to do is solve a system of equations. So I have x plus y equals to 1. Now, I probably am going to use Gauss Jordan for this. So what I'm going to do to solve this, so what I'm going to do to these equations is I need the x's together and the y's together. Okay, So that means up here, I'm going to subtract x on both sides, and I'm going to, on equation 2, I'm going to subtract y on both sides, so that I'm going to have zeros after the equals. So this is going to be negative 0.2x plus 0.6y equals 0, and then it's going to be 0.2x minus 0.6y equals 0. Okay, so that's what I want to solve. So I'm going to use the row operations to do this. So if I put this into a matrix, nicely I've lined up the x's and the y's. So it's going to be 1, negative 0.2, positive 0.2, 1, I'm going down the columns, negative 0.6, my line, and then 1, 0, 0. Okay, so normally we start with the pivot and use that to change the rows below it. But because I see that these rows actually look very similar, my first operation I'm going to do is just I'm going to change row 3 by adding row 2 to it. Okay, so row 2 is not changing. Okay, now if I add the entries from row 3 to row 2, I'm going to have a 0, a 0, and a 0. Okay, so this actually will always happen, but we'll talk about that in a minute. Okay, so now I'm going to keep going with the regular row reduction. So I want to change, so I'm pivoting around this 1, so I want to change that negative 0.2 to be a 0, so I'm going to do row 2 plus 0.2 of row 1. Okay, so my 1, 1, 1 stays the same. This one's going to become a 0. Okay, I still have the row of zeros. 0.6 plus 0.2 times 1, that's going to be 0.8. And 0 plus 0.2 times 1, that's going to be 0.2. Okay, so now I want to move down 1 over 1, and I want to pivot here. So my next step is going to be row 2 divided by 0.8. So this is now going to be a 1. And 0.2 divided by 0.8 is actually 1 over 4, or 0.25. Okay, and now I'm still pivoting here. Okay, but I have one more step. Row 1 minus row 2. Oh, shoot, I'm changing row 1. Sorry, I got ahead of myself there. Row 2 is not changing. Neither is row 3. Okay, so 1 minus 0 is 1. 1 minus 1 is 0. And 1 minus 0.25 is 0.75. Okay, now we remember that this was the x column, this was the y column. So I'm in diagonal form with an extra row of zeros. So I'm going to have my solution is x equals 0.75 and y equals 0.25. Okay, now remember that the x, y were the places, the sort of entries in S. So S is the matrix with x and then y, which means that it's the matrix 0.75, 0.25. And remember, it's in the order D, B. Okay, so now we found the same S as we had before. Okay, so what did we just do? Okay, so I sort of, on the next page, I wrote this method. So this is to determine long-run behavior. Okay, so the question might ask you, in the long run, what do you think will happen? Or what's the probability that this happens? Or it might say, eventually, what's the probability that this thing happens? Okay, so for regular Markov chains, we know that we can predict this behavior. So what you want to do, if you're looking for long-term behavior, is you want to find your transition matrix, okay, and make sure that it's regular. Okay, often they're going to be all positive, but if it's not, you're going to have to check that it's regular. Then, because it's regular, it definitely is going to have a stationary matrix. Okay, I called them S1, S2, S1, S2, S3. If you want to use XY or whatever, XY and XYZ, okay, go ahead. It depends on how many states you have, which one you use. Okay, it could be more. It could be 4 of them. So that you know the stationary matrix exists. So you just let it be this. And then you know that it satisfies the equation S times P equals S. Okay, so you want to write that out, simplify, so multiply the matrices on the left, okay, and then find the resulting system of equations. Okay, so that's what we did. Now, the next step says you can discard one of these equations. Okay, why can you do that? That's because they always have extra information. Okay, so if there's two, one of them should be a multiple of the other. Okay, so they're going to cancel each other out. So this row we did not need to have in our row reduction. Okay, so you're allowed to throw one of them away. Okay, so if, maybe I'll just write here, okay, if you don't, and you row reduce, oops, you will just get a row of zeros, which doesn't affect the solution, okay? So you don't have to throw it away, but it's better if you do, and especially if you're going to use a different method to solve, okay? So if you're not going to row reduce, if you're going to use, say, substitution, it might confuse you because you're going to have more equations than you need. Okay, so it's good to throw one of these out. I would say do it. Pick your least favorite one and throw it away. Now, what you need to remember to do, maybe I'll highlight this, is you have to add the equation. X plus y equals 1, or S1 plus S2 equals 1, or the other one if you have 3, okay? You must add this. Okay, so you get to throw one of the bad equations away, but you have to add in this nice one. Okay, and then you want to solve the system. So you can use row reduction, you can use substitution, you can use inverses, okay? Because it's regular, you know there's going to be a unique solution. So if you want to use inverses, you can. One comment, if you're using row reduction, remember to move all the variables to one side, to the left side, because you're going to have your variables on the left and the right. Okay, so before you can enter it into a matrix, you need them all on the same side. And when you row reduce, if you do that, your matrix, okay, put the nice equation on top. So you're going to have a row of ones on top. Okay, and then all your other equations are not nice, but they all are going to end with zeros. Okay, so that your matrix that you row reduce should look something like this. Okay, it's best, you don't have to, but it's best if you put the x plus y equals 1 / x plus y plus z equals 1, that equation on the top. Because it's already 1, it's going to make your life a little bit easier. So that's how you find the stationary matrix. Now some properties for regular Markov chains. So if you have transition matrix P, okay, for a regular Markov chain, there's a unique stationary matrix, okay, that satisfies this equation. Now notice when we found the other one, we did not use S0. Okay, so we always approach S no matter where the system starts. Okay, so we did not, maybe I'll write that here. Okay, so we did not use S0 when finding S. Okay, so it doesn't matter where the system starts, you're always going to end up approaching S. You also get this, so P to the power K, because Sk is equal to S0 times P to the K. If if Sk approaches S, so some stationary matrix, then P to the K has to approach something as well. So this thing we call P bar. Okay, it's called the limiting matrix. And what it looks like is actually really easy. So it's going to be an n by n, okay, just like P. But in every row, it has your stationary matrix S. Okay, so maybe I'll just write that. So every row is the stationary matrix S. Now, why is that? Well, remember that the rows are indexed with the current state, so the state at the beginning, and the probabilities are the probability that you end up in a given state after k steps for p to the k. So because sk does not depend on S0, it doesn't matter where you start. The chances, no matter where you start, the chances that you end up in a particular state are the same. So the probabilities are the same. Okay, so it's going to be matrix S for every single row.